So let's look at this cyclic phosphorylation and the non-cyclic phosphorylation in detail such that we basically understand it quite well. Cyclic phosphorylation is it involves photosystem 1. That is a fact. That means that you need to know that actually. So what happens? Still the same process. Electrons are excited by the light energy, and then they are passed through a series of electron carriers, and the examples are here: plastoquinone, and then cytochrome, and then plastocyanin. These are examples of electron carriers that are involved. So that means that the electrons move through them, and then they will return back to photosystem 1. Okay, so as the electrons are moving through that electron transport chain, you will have energy being released, and that energy is sufficient for the synthesis of ATP that will actually drive what we call the proton pump, or that will pump the protons here from the stroma into the thylakoid space. Okay, that energy that these electrons are releasing is sufficient to drive the proton pump, and that proton pump mechanism actually very much creates a proton gradient across the thylakoid membrane, and this high concentration of hydrogen ions, remember the hydrogen ions or the protons basically are being pumped into the thylakoid space. That means that you're going to have a gradient, an electrochemical gradient, and that electrochemical gradient is what will make the protons to diffuse back into the stroma through a complex called the ATP synthase, okay, which is a complex protein in the membrane. So this movement of the protons is what drives the synthesis of ATP from ADP. Okay, that means that you have ADP combining with inorganic phosphate to form ATP, and that process is what gives us the ATP that we are interested in through a process called chemiosmosis. Chemiosmosis. Okay, so this ATP will later on be used in the light independent phase of photosynthesis. That is the Calvin cycle, as we shall see later on. And it is that ATP that will be used in the reduction of carbon dioxide into carbohydrates. Okay, so just a summary of cyclic phosphorylation. Cyclic phosphorylation happens in the photosystem 1. Okay, when light strikes photosystem 1, you'll have electrons getting excited, and they will move to higher energy levels, and they will be carried by a number of electron carriers. Okay, as the electrons move back to photosystem 1, they release energy, and that energy is sufficient to cause proton pump. That proton pump is the one that creates a proton gradient, and because of this, you will have high proton concentration in the thylakoid space, and this creates an electrochemical gradient. This electrochemical gradient means it is possible for the protons to diffuse back into the stroma. Remember, they were being pumped out of the stroma into the thylakoid space. Now, because of the high concentration of the hydrogen ions, the protons basically, you will have them diffusing back into the stroma through the ATP synthase, and then this will be what the movement of these protons will be the one you use to drive the synthesis of ATP from ADP and the inorganic phosphate, and the process is called chemosmosis. Okay, chemosmosis, and this ATP can be used in the process of light independent stage of photosynthesis. Okay, so the non-cyclic phosphorylation, this involves both photosystems, photosystem 1 and photosystem 2. The electrons follow in one direction. That's what we mean by unidirectionally, from photosystem 2 to photosystem 1 through a chain of carriers. And still, you will have photolysis of water happening. That means water is being split. This is very important to create, to basically feeding or to fill in the electrons that have been lost at photosystem 2 as the electrons are getting excited. Okay, so we get electrons and also get protons from photolysis of water, but we also get oxygen, which is a byproduct or waste product of photosynthesis. Okay, the electrons from photosystem 1 are passed to NADP to form the reduced form of NADP and ATP synthesis. That is basically for emphasis reasons. So what's the difference between phosphorylation and maybe before we go to the phosphorylation, the differences, we can look at the similarities. In both cases, cyclic and non-cyclic phosphorylation, you have electrons the electrons get excited, then they are carried along different electron carriers. Okay, and these involve pigments, photosynthetic pigments. Eventually, when these electrons come back, you have sufficient energy to form ATP, and this all happen in the thylakoid membranes, and it actually drives proton movement across the membranes. Okay, so coming to the differences, cyclic means that basically cyclic phosphorylation involves photosystem 1. That means that the electrons have to come back to photosystem 1. Okay, you don't have anything to do with photolysis of water. Why? Because photolysis of water only happens because the electrons in photosystem 2 have to be replaced. So that replacement happens when you have the water splitting, okay, to fill in the electrons. Okay, so that means that eventually with non-cyclic phosphorylation, you will have the final accept of electrons being the NADP, and that is basically the reduced form of NADP. Okay, and then with the cyclic phosphorylation, you will have photosystem 1 being the last electron acceptor. Okay, and that's what we have there. So that marks the end of this presentation about the light dependent phase. This phase depends on light, and that's why we call it photochemical reactions. And that's why perhaps we also call it the light stage. It involves mainly two processes: oxidative phosphorylation and then the formation of the reduced form of NADP, which is nicotinamide adenosine diphosphate, the reduced form. Another key important thing is photolysis, which is where water is actually split into protons, electrons, and oxygen, and that oxygen is a byproduct of photosynthesis. Thank you. Remove your lights. Let me go and rest.